So here's our situation for 23. We have this uniform plank, meaning it's the same from end to end, with a length of 2 meters. The length of the plank is 2 meters, and its mass is 30 kilograms. Where are we going to draw in the weight of the plank? If it's the same from end to end, nice and uniform, where do we put mg for the plank? Directly in the middle, right? Like that. Supported by 3 ropes. So we have 2 ropes on the left and 1 rope on the right, and they're already labeled for us. Rope 1, rope 2, rope 3, right? Tension 1, tension 2, tension 3. And what else do we have? We have a 700 Newton person standing half a meter from the left end. So this is going to be 700 Newtons down like that. Okay, so what we're trying to find are the 3 tensions. Find tension 1, tension 2, and tension 3. So what I'm going to do is I'm actually going to erase this. We're going to do a free body diagram for the plank. So I'm going to get rid of this and just kind of redraw it. Okay, so here is the plank. Like that. Okay, so what are the forces acting on the plank? Let's start over here on the right. On the right we have rope 1. So tension 1, they told us that this is at a 40-degree angle. Like that. Okay, the weight of the plank itself goes in the middle. Boom. So we got to convert this to newtons, right? They told us it's 30 kilograms. So are we just going to go 30 kilograms like that? That's not a force. So what's it going to be? 30 times 9.8 mg. So this comes out as 294. Okay, then we got this person standing here on the plank. So that's a force on the plank. His weight, it's already in newtons. They gave it to us here in newtons. A very common question I've heard many, many, many times. Students will ask, they're like, well, hey, isn't there also a normal force? Anybody have that thought? No? Well, you guys are smart. Look, why do we not want to show normal force here? Are we doing a free body diagram for the plank or for the person? For the plank. This guy right here is simply a force on the plank. So don't put normal force on there. Normal force is a force on the person, not on the plank. Okay, now we have a rope to the left. They label that was given as tension 3, and then we have tension 2 pointing straight up. Okay, this problem involves torque. Whenever you do torque, you have to include distances on your diagram. Okay? In order to put down distances, you need to have an axis. The best place to put your axis is at the point where you have the most unknown forces, which is right here. So we're going to say that the left end of the board is going to be defined as our axis. Okay? Now why is that going to be nice? That's going to be nice because tension 2 and tension 3 will not appear in our torque equation. When we sum the torques, we're not going to have tension 2 and tension 3 there. They're going to disappear. Why will they disappear? Because forces on the axis cause no torque. Okay? So let's put our distances down. We'll do this in red. Or not. There we go. All right, so the total length of the plank, the whole length is 2 meters. All the way across. Okay, what's the distance to the middle of the plank? 1 meter. And then scoot this out of the way. And then the distance over to the guy, to right there, that's 0.5 meters. Okay, so these are our distances. Now, let's write the equations. So look at, we have 3 equations. We have 3 unknowns. Go back to black. We have 3 unknowns. T1 is a question mark. T2 is a question mark. T3 is a question mark. if you have 3 equations, you need to have 3, wait, I can't talk today. If you have 3 unknowns, you need to have 3 equations. So how are we going to get 3 equations? I'm going to make some room here. Okay, so we're going to go like this. We sum forces x. How many x forces do we have? 2. We have the x component of T1, and we have T3. Okay, so this is going to be, we're going to go cosine 40 T1. That's the x component of T1. And then minus T3 equals ma. Sum of the forces always equals ma. But is there an acceleration? No. So this goes to 0. Boom. We just wrote an awesome equation. Okay. Now we sum the forces in the y. Summing the forces in the y direction. We have 4 forces in the y. We have 1, the y component of T1, that's 2, and then 3, 4. There's 4 y forces. All right, so here's what this looks like. You're going to go T2 plus the y component of T1 is sine 40 T1, and then minus, let's just add these together. 700 plus 294, that's 994. Okay, so we added up the y forces. They cancel to 0 because there's no acceleration. Now, the final thing is to sum the torques. How many torques are on this beam, or on this board? So the axis is right here. Here's the axis. How many torques do we have? 1, 2, 3. And then these guys, T2 and T3, cause no torque because they're on the axis. Okay? Now what's the sign convention for torque? Is it going to be up, plus, down, minus? It's clockwise, counterclockwise. All right, which way is T1 acting on the board? Clockwise or counterclockwise? Counterclockwise. It's pulling up like that, kind of. I mean, I know it's to the right, but still, it's kind of like, you know, it's yanking up on the board, which is going to be counterclockwise. Does that make sense? Okay, so it's counterclockwise. Then these guys are clockwise, right? Because they're pulling down on the board. Hey, whenever you're figuring out clockwise, counterclockwise, you have to know where the axis is. You can't figure out clockwise, counterclockwise without knowing where the axis is. You know, axis right there. These 2 guys are pulling down. Okay, so should we say counterclockwise is plus? It doesn't matter which one's plus. Let's say that counterclockwise is plus, and then clockwise is minus. Let's just go with that. Okay, T1 is going to be tricky because why? Is T1 perpendicular to the board? No, you like this. 2, so this distance here, this distance right here is 2 meters, but is 2 meters perpendicular to T1? So look, you can either make the force perpendicular to the distance, or you could make the distance perpendicular to the force, like that. That would be acceptable. You could like that. Let's make the force perpendicular to the distance. So here's what you do. Let's go red. Do this in red. So look, T1 has x component, y component. Notice that this y component, is that y component perpendicular to the board? Yeah. That y component is sine 40 T1. Everybody see that? And that's what we're going to use. We'll use sine 40 T1. Okay, so you're going to go like this. So sine 40 T1. That's the force. Now what's the distance? What's the distance perpendicular to that? 2 meters. So now we made them perpendicular. It's money. Okay, now minus, let's do 294. 294. What's the distance perpendicular to that? From the axis, what's the distance from there to there? 1. So that's going to be 294 times 1 meter. Okay, now let's go to the 700. Minus 700, what's the distance for the 700? 0.5. That's it. Okay, what will happen to the torques in this class? They will cancel to 0. Now what happens if they don't cancel to 0, just so you're smart? What happens if the torques don't cancel? What would be happening? It'd be rotating with an angular acceleration. Okay, but that's not going to happen. Okay, so here the rest is algebra. Now we can take this last equation. What's the only thing missing in that last equation? T1, and by the way, that's why we put the axis over here. So that way T2 and T3 would disappear, right? So T1, when you do the algebra, you get about 501. Comes out about 501. Now, take T1, plug it in there, and there. And now you can find T2 and T3. Right? So in plugging T1 in, now you can get T2. T2 comes out as 672. And then go up here. T3 comes out as 384, about 383.7. So the rest is just algebra once you have the equation set up.